the IIPT member, today's eminent speaker, Professor Joseph Samir, my teacher colleague, and all dear students for this lecture series. This online lecture series is the joint effort by Physics Department of Somaya College and IIPT Mumbai. It will be conducted on every Thursday from 23rd July to 27th August, containing total 6 lectures on various interesting topics in astrophysics and other branches in physics. Dear friend, due to this pandemic epidemic of corona, the college is closed, but we teacher always thought about you. So choosing this interesting topic and the eminent speakers from the various fields. Thanks to Shekhar sir and his team member for the effort they had taken. I am sure that you all feel enriched with the knowledge after completion of this lecture series. Before we start, let me introduce our department in short, just within the 2 lines. Our department established in 1960, that is from the starting of the KJ Somaya College, it is the oldest department in college. We started with highly qualified, devoted faculty, expert, and supportive staffs. Our department had 50 dedicated teachers and more than 600 students. Apart from the curriculum, we offer 3 certificate courses on astrophysics, astronomy, embedded system, and nanotechnology. Our students actively involved in various research activities. Our research, our yearly activities for the student up till now was the workshop, seminar, alumni interaction, remedial coaching, bridge course, light show, which is the exhibition of the light-based experiments, intercollegiate festival, that is the various competitions, photography, poster, quiz, crossword, Bob the Builder, and so many are there. This year, due to lockdown, we can't able to do this, but still we are there for you. I don't know when our college will start, but still we started the program. We had an 7 days online course. We had the alumni interaction also online, and this is the lecture series which we are starting from today. Friends, this online lecture series also you will be enjoyed and enriched. Thanks to Principal Madam for giving the immediate permission for and all help for arranging this lecture series. She has been our inspiration and mentor in organizing such events. Thanks to all the IIPT members for all the help they provide for hosting this program on the banner of Physics Department of Somaya College. Special thanks to our eminent speaker today and his interesting topic of mystery of the extraordinary life and mysterious disappearance of Ettore Majorana and his elusive particle. Again, thanks to Shekhar sir and his team member and all my participant student friends. I hope you all will enjoy this program on every Thursday. Thank you very much.
Thank you, madam. Now I call upon uh, Dr. Atul Modi, President, IIPT Mumbai Sub-Regional Council, to give his welcome address. Atul.
Good evening, everybody. Welcome to the second series of IIPT lectures this season. Mumbai IIPT is one of the active IIPT bodies. IIPT, Indian Association of Physics Teacher, was founded by late Professor D.P. Khandelwal with an intention of creating a benchmark for physics education, and also what IIPT has started is national standard examinations in physics, also conducts chemistry and biology, astronomy. These exams serve as the first round of selection for Olympiad program of India. IIPT also conducts national graduate physics examination. The intention of conducting this exam is to create a national standard for undergraduate physics education and a benchmark. Uh, Students who top national graduate physics examination, top 1% at all India level, are also eligible for some of the prestigious institutes' integrated PhD programs. We very much thank KJ Somaya College for taking responsibility of hosting this set of 6 lectures for IAPT. Uh, Primarily, we conduct this program for undergraduate students, but definitely it is very enriching for teachers as well, whether it is school teachers, junior college teachers, degree college teachers, everyone alike. So over to you, Shekhar.
Thank you, Atul. Okay. Now I have the pleasure of inviting Professor Vijay Singh. It's always a pleasure to hear him. Sir.
Hello, thank you, Shekhar. Am I clear?
Yes, sir.
Yeah.
Oh, thank you. So, yes, actually, the IAPT and several things have been said about IAPT by Dr. Atul Modi. So I would only like to add that the IAPT has about 8,500 members spread across India and about 100 members abroad. Uh, Besides running these national standards exams, the IAPT runs a large number of programs and now webinars in all parts of the country. So it happens to be the largest voluntary, democratic, grassroots body of science teachers in India. Having said that, let me now come to today's function. It has been my privilege to work with two eminent members, I would say, who are in the audience today, Dr. Pragya Prabhu and Dr. Joseph Samuel. I have very pleasant memories of 2013 of working with Dr. Pragya Prabhu in organizing the Junior Science Olympiad camp for students, for 30 or 40 students at Somaya College. And we were very grateful at that time that Somaya College took up this responsibility, and it was discharged with great, I would say, circumspection and with great sense of responsibility by Dr. Pragya Prabhu and her colleagues. So once again, from 2013, very happy memories, and thank you, Dr. Prabhu. I've also this pleasant task to say a few words about, how should I say, about Joseph Samuels. In 2014-15, I had the privilege of working with him. He was the chairperson of the academic program, I think theory, for the International Physics Olympiad 2015. And we had several sessions from which I got to learn a great deal from him. And he's a wonderful speaker. He does not obfuscate. He says things in a very simple way. So I'm sure that we will all understand today's lecture, and I'm looking forward to hearing from him. Thank you, Dr. Samuel. And finally, I would like to thank Shekhar, the Bombay SRC, Sub-Regional Council of Bombay IIPT, and above all, the Somaya College for hosting this series of webinars. So thank you. Over to you, Shekhar.
Thank you, sir. Okay. Now I call upon Principal Madam to give her inaugural address, so we can go ahead. Yeah.
Thank you so much, Professor Singh, sir. I'm so delighted to see you here, and then it was really learning experience for me, and I really mean your words. Thank you so much. Thank you so much. Very good afternoon to everybody, and welcome all to this lecture series organized by our Department of Physics in collaboration with IIPT Mumbai Sub-Regional Council. I'll take the opportunity to talk a little about my college, because our physics department and Shekhar and his team is hosting this lecture series. I am really happy about it. KJ Somaya College of Science is one of the colleges under Somaya Vidya Vihar Trust, almost 60 years old, one of the reputed colleges in Mumbai. We are autonomous and affiliated to University of Mumbai with A grade by NAC 3 times. It is located at Vidya Vihar, as there are many participants from outside. There are almost 100 participants. I would like to talk about it. In 60 acres of lush green campus at Vidya Vihar, We cater around 15 undergraduate programs, 14 different postgraduate and 5 PhD programs, and almost 5,000 students strength of our college, as we also have the junior college. We are the recipient of prestigious DST FIST grant, Star DBT grant, and also our college has been identified as college with potential for excellence in 2016 by UGC. Today, we are really honored to have with us an eminent personality, Professor Joseph Samuel, a renowned physicist, to deliver the first lecture in this series. Thank you so much, sir, for accepting our invitation. And we all look forward to this, learn from you. I also welcome Dr. Atul Modi, who is president of Mumbai region IAPT. Thank you for giving us this opportunity. And I also thank my physics team, particularly Shekhar, who has taken the initiative, and all other colleagues of Shekhar, Ketan, and even Ranjana madam, and all others. Thanks to all the participants. I can see now almost 100 participants have joined. And thank you all. Welcome to everybody. And I declare that the inauguration, this event has been inaugurated. Thank you so much. Thank you, Shekhar.
Thank you, madam. Okay, now I have pleasant duty of introducing our today's speaker, Professor Joseph Samuel. Uh, Let me begin with it. So, Professor Joseph Samuel has done his integrated masters in physics from IIT Kanpur. Then he went on to do his PhD from Indian Institute of Science. His topic was Hamiltonian mechanics. Then he joined as a faculty at Raman Research Institute. And now he is Professor Emeritus at Raman Research Institute and ICTS TIFR. He has a Simon Fellowship. His area of interest are classical mechanics, geometric phase in quantum mechanics, general relativity, and topology in physics, quantum information and entanglement, and quantum gravity. He has done a lot of work on science popularization at various levels. Okay. And one more very important thing where I met Professor Joseph Samuel, he's a very sweet and person, uh, was at Homiva Center for Science Education. So he was the chair, he chaired the National Academic Committee of IPHO 2015, which was held in India. So we welcome Professor Joseph Samuel, and sir, it's all yours. You can start your talk.
Thank you, Shekhar. Let me first share my screen and put up the slides.
Yes.
So before I start, am I really audible?
Yes, sir.
Yeah,
Okay.
yeah.
So first, I'd like to thank IPTA, Physics Teachers Association, for this opportunity to talk to all of you. Particularly like to thank Shekhar and Mahesh Shetty and all the nice people that I've been listening to now, Ranjana ma'am and the principal, and Atul Modi. Okay, I think I should do something to maximize this. Let's do that. Okay, is the screen visible to you?
Yes,
Yes.
yes, it
Okay.
is.
So,
Yeah.
All right.
so the title of my talk is The Enduring Mystery of Ettore Majorana and His Elusive Particles. So this is a very interesting character, and I think all of you will be, well, if you don't know about him already, will be heartened to know that there are strange people in physics who are very deep in some ways, but also it's a tragic story as well. So here's a picture of Ettore Majorana. Yeah. So this is a picture and of a photograph of him taken at a studio. He was born in the year 1906. And we don't know the year of his death. You can see a question mark where there should be the year of his death. And that is the mystery of the man. We really don't know when he died. But during his short life, he was able to achieve quite a lot in physics. And I'm using this biography and the mystery of the man as a kind of hook to interest all of you in the story which I'm going to tell. Of course, there's going to be physics later in the talk, but the idea behind the man is that the mystery itself is so enticing that I would like to draw you in with this mystery and then go on to tell you about some of the physics that he did in terms which I think would be understandable to a bachelor student. Towards the end, the level will go slightly up, and I hope that master students will be able to follow that part of the talk. But I think the faculty will have no trouble with all of everything that I'm saying. And it is my pleasure that I'm talking to all of you. It's a pleasure to see Vijay again. And all of you who took the trouble to come to this talk, thank you. And I hope you're safe, and I hope that you will stay safe. So the plan of the talk is, first, as I mentioned earlier, I'm going to talk about his biography. That is his life story, which itself is quite an interesting one. And next, I will talk about Fermi's opinion of Majorana. You all know that Fermi was a scientist of the first caliber, but he places Majorana in a class far above himself. Then about the physics, I'm going to talk in increasing order of abstraction and difficulty. First about the neutron discovery and Majorana's role in this discovery, slight as it was. Second, I'm going to talk about the Landau-Zener problem. This is a problem on which Majorana worked with distinction. And finally, the most famous of his works, it's about the idea of Majorana particles. And I'll give a very brief conclusion. So let me take a look at the time. I'm starting at about 4:20, I think. So I will go on for about an hour or so. Now, one of the problems with online talks is that I cannot see the reaction from people. I can see a few faces here. So I would very much appreciate it if there are questions. So the way to ask a question is to use the chat line. And I think the question will be transmitted to me by one of the organizers. And then I will try to answer. That way I get a good idea of what you are thinking about. And honestly, if I don't get to the end of my talk, I really don't mind. I'd like to just be clear and communicative throughout the talk. I hope that is clear. So what I've done is, inside the talk, I've put in a few slides with a big question mark. So those are pauses for questions. I would encourage you to ask questions during that time. And as I said, it doesn't matter that I don't cover my material. The material probably would last for an hour and 10 minutes or so, but let's not worry about it. So Majorana was born in Sicily, the island of Sicily, which is just off the toe of Italy in 1906, in a small town called Catania. Around the age of 16, he started studying engineering, but during his studies, he was enticed by physics and he switched in 1928 to the physics stream without completing his engineering. He had an encouragement from some of his friends, Emilio Segre, and his initial work was on atomic spectra. So that's the time at which quantum mechanics was used to understand atoms, after the Bohr atom and all that. It was getting into more quantitative descriptions of atoms. In 1931, he worked on the Thomas Fermi model to understand the experimentally observed spectra of gadolinium, uranium, cesium. And in 1932, he took up the problem of atoms in time-varying magnetic fields and radio frequency spectroscopy. We'll talk about the atoms in time-varying fields later. That's one of the physics topics I want to talk about. In 1932, there was an interesting experiment performed by Bothe and Becker and repeated by Irene and Julia Curie, who had misinterpreted their results. Now, Majorana had a key role to play in the correct elucidation of this experiment, which is another of the topics that I will talk about. In 1932, he went on to discover some infinite dimensional representations of the Lorentz group. That's obscure work, which I will not be talking about. I mean, obscure to our present context. Now, in 1933, he got a fellowship to travel around Europe to visit various laboratories. So he went to Leipzig to work with Heisenberg. He seems to have hit it off very well with Heisenberg. They were good friends and they worked happily together. He worked on nuclear models with Heisenberg, and he also visited Niels Bohr in Copenhagen. In 1933, in the fall, he returned to Rome, and he was a changed man for reasons we don't fully understand. He was suffering from gastritis, and that's a disease, that's a problem that afflicts people who are under severe stress. Your digestive system starts backing up, and there's a lot of acidity in the stomach. And he was also in a state of nervous exhaustion. We don't know why he was in this state. He grew reclusive. He withdrew from his colleagues, his family, and his friends, stopped coming into work, stopped publishing. He never left home. And in this period, he worked on a range of subjects. He had some interest in philosophy. He worked on geophysics, electrical engineering, mathematics, relativity. The unpublished work from this period has since been published posthumously. Important work from this period is about the new representations of the Lorentz group, which I will not be talking about. In 1937, Fermi arranged for a professorship at the University of Naples. Actually, around the time of 1937, there were some professorships for which one could apply. And in fact, he applied for it. But he was so far above in stature from the other participants that they decided that the other applicants will go through a separate channel, and they created a special professorship for him at Naples, at the University of Naples. And he went on to teach very enthusiastically at the University of Naples. But after a few months on the job, he disappeared. And the director of the university where he was working, one Mr. Carelli, received a note, which I will read out in full. Let me see how I'm doing on time. Yeah. I made a decision that has become unavoidable. There isn't a bit of selfishness in it, but I realize what trouble my sudden disappearance will cause you and the students. For this as well, I beg your forgiveness, but especially for betraying the trust, the sincere friendship, and the sympathy you gave me over the past months. I ask you to remember me to all those I learned to know and appreciate in your institute, especially Shruti, one of his friends at the institute. I will keep a fond memory of them all at least until 11 p.m. tonight, possibly later. Ettore Majorana. Now, this is a disturbing note. When you say that I will keep a memory of them at least until 11 p.m. tonight, it sounds like something dramatic is going to happen at 11 p.m. that night. This message was immediately followed, almost immediately, by another message saying that he'd cancelled his plans. This sequence of messages was sufficiently disturbing to the director, Mr. Carelli, for him to let the ambulance pass, solve coronavirus around here. Yeah. He contacted the family of Majorana and they started searching for him all over the place. They could not find him. He was never again seen by any of his friends or family. What is known is that before he disappeared, he withdrew his money from his bank, all the money that was in his bank. He traveled to Palermo in Sicily, which is his native island. Then he bought a ticket from Palermo to Naples. It's also known that he got on the boat. It is not known if he got off the boat at Naples. It's possible that he committed suicide by jumping overboard the boat. But the body has never been found. So this is the mystery of Majorana. What happened to him? He left a note to his family at the hotel in Palermo. I have only one wish. I do not wear black. If you must conform to custom, just wear some emblem of mourning, but not for more than 3 days. After that, remember me in your hearts if you can, and forgive me. Very touching note. There are many theories about his disappearance, the most common being suicide. And that was the commonly held view until the early part of this century. For about 75 years, there was no further developments of this case. And he was on the missing persons register in Rome. Now, in 2008, there was a TV show designed to pick out missing persons. If a person was missing, the family could write to the show and they would put up a photograph of this guy with a description. And then somebody or the other could call in. Somebody who had seen him could call in and say that I've seen this person either in Rome or Paris or wherever he has seen him. This show was called Who Has Seen Him in Italian, Che ha visto. The caller was Roberto Fasani, a Sicilian who went to Argentina in the 1950s. He met one Signor Bini through another Sicilian friend. And the Signor Bini was about 50 to 55 years old. He had white hair, but it's possible that he was the same person with black hair turned white, just like mine. I'm not comparing myself. A Sicilian friend who presented me to a Mr. Bini connected Bini to Majorana, thanks to Carlo, an Argentinian. He said, do you realize who that is? He's a scientist. He's got a brain you can't imagine. He's Signor Majorana. So this was directly from Carlo to the Fasani. He was living in Caracas, according to Fasani, he was living in Caracas, which is in Venezuela, living in relative poverty, working as an engineer. Fasani saw in his possession a postcard dated 1920 from Quirino Majorana. Now, Quirino Majorana was an uncle of Ettore Majorana, an experimental physicist, and he might have had some of the inspiration for Ettore to switch into physics. So this fact also lends some credence to this whole story. And there's also a photograph on the left, you can see Fasani, and on the right, our right, you can see Signor Bini. And they're just outside a bank. This photograph was taken at a time when Bini was trying to borrow some money from Fasani because he was always in monetary distress because he was not very well off in Venezuela. The face characteristics from this photograph match Ettore's and his father's. There are experts who can tell you how a person will age with time. And according to these experts, it's consistent. This photograph is consistent with this being Ettore Majorana under an assumed name. And when these details came out, the case in the coroner's court in Rome was closed. They said he was a missing person, but now we know that he left of his own accord. It was his own voluntary choice. Let's close the case. But it's never been completely confirmed. For example, there is no grave of Signor Bini found in Venezuela. And to the best of our knowledge, he had not gotten married or had children. If there had been descendants, we could have done a DNA test to confirm that it was in fact Signor Majorana, but we don't know for sure that the story is the right one. So we will never know really, but there are only theories, and some of the theories are absurd to the point of being wacky, but this one seems to me to have some substance. We don't know the motives for his disappearance. And this is the first point at which I will close. I will just pause to get some questions from the students if possible, to get some comments from anybody who would like to offer comments, especially from the students. So it's a good time for me to drink some water.
Pallavi, any questions there in the chat box?
Okay, so it looks like there are no questions.
Yes, sir. There seem to be no questions for now.
So let's go on.
Yeah.
So the next topic I'm going to cover is Fermi's regard for Majorana. I'm slowly going from personalities towards the physics. So I already mentioned that Fermi had arranged a professorship for Majorana. This is an evidence of his intense regard for Majorana's abilities as a physicist. And just after Majorana went missing, Fermi told one of the people who was there in his lab, saying that, there are many people in this world who work very hard and do reasonable physics who don't get anywhere at all. And there are others who are extremely successful as physicists, and Fermi himself was in that class. And they have a class. They have a certain standing in the community. But he said Ettore Majorana is a different class from everybody. He's a sheer genius. He's in the Newton or Galileo class. It's not every day that you can find a person like him. And it's not a gift that's given to everyone. He had a very high regard for Majorana. And this is no mean compliment coming from Fermi. Later, during the bomb project in Los Alamos, whenever they hit a problem, there was often the cry that went up from the Italians, I wish Ettore were here. And when this cry went up very frequently, General Groves, who was the military director of this project at Los Alamos, he asked, who's this Ettore? Can we get him into the program? And Wigner told him, no, unfortunately we cannot. He's disappeared. So that's an example of how highly he was regarded by the community. Because, you will see later that he had a brain that could wrestle with experimental details as well as theoretical speculation. It's an amazing range of expertise in one person. His study notes were such that he was deriving everything from scratch. Whenever he studied something, every little thing was there. We all know that when we want to look up something, we go to the web and look up this and that and incorporate, the Raka coefficients from one place and Claire's coordinates from another. This guy was well in touch with experiments, and this is a characteristic of the Fermi school, but he'd also mastered the mathematics of his time, whether it was complex analysis or relativity or group theory. In fact, in those days, many people regarded group theory as the pest which had infested physics, which had polluted what was a very, very sensible activity with irrelevant mathematics. There was a German term called the Gruppenpest, and many people dismissed the Gruppenpest. He didn't do that. He mastered group theory. He anticipated several developments which are still going on in physics, within the world of physics. His character was such that he never sought credit for his ideas. Whenever he had understood something, he regarded it as trivial. He never pursued it further and tried to make a big noise about it. He wrote a total of about 9 or 10 papers, most of them in Italian. And a lot of those papers were completely ignored until they became recognized as relevant. Now, the mystery regarding Majorana's disappearance may never be resolved, but there is much to admire and much to learn from his life's work. He was before his time. He casts a long shadow, and his name appears in several branches of physics today. That's what we're going to get to next. So the topics I'm going to cover, now we're passing to the physics part of the talk. The discovery of the neutron, atoms and magnetic fields, and actually the adiabatic theorem in the context of the problem of atoms and magnetic fields. And finally, the most famous discovery of his, Majorana particles, which is still an ongoing topic of research. Now, the discovery of the neutron is usually credited to James Chadwick. And indeed, he deserves credit for this discovery. He got the Nobel Prize in 1935. But there's an interesting backstory to this discovery. There was a bit of confusion before James Chadwick appeared on the scene and cleared it all up. You know that physicists like to hit things against other things to learn what is inside. This is what all physicists do in accelerators. they hit particles against one another. In those days, things which are available were things that you could get out of the nucleus by radioactivity. So for example, alpha particles were a popular thing. Alpha particles are helium nuclei, and they were used to hit other nuclei with this, to learn what is inside. And physicists are like children. You know that if children are given toys, they'll hit the toys and break them and find out what is inside them. If you give a child an unbreakable toy, he will use the unbreakable toy to break the other toys and find out what is inside those toys. That's exactly what is going on with the helium nucleus. So there was a group of Germans, Botha and Becker in 1930, who were hitting light nuclei with helium nuclei, with alpha particles, with the lightest nuclei. This is the example of hitting one toy with another toy. So they were bombarding light nuclei with alpha particles, which are helium nuclei. And what they found was that some very penetrating radiation emerged from the collision. They didn't know what it was. They published their results. What they found was that the radiation that came out was not deflected by electrical fields. At that time, they only, Vijay, you'd like to say something? The radiation is not deflected by electric fields. At that time, the only known nuclear radiation were alpha, beta, and gamma. Alpha was helium nuclei, beta was electrons, and gamma was photons emerging from the nucleus. So they concluded that the reaction which must be happening in the case of beryllium, which was one of the strongest sources of this radiation, was that the helium nucleus collided with the beryllium nucleus to produce carbon-13 plus a very energetic photon, which is a gamma ray. Gamma rays are photons that emerge from the nucleus. There's no fundamental difference between X-rays and gamma rays, except that X-rays come from the atom, while gamma rays come from the nucleus. So this was their explanation for what they had seen. Gamma rays, being neutral, are not deflected by electrical fields, and they have an enormous penetrating power if the gamma ray energy is high enough. So that was their conclusion. Irene and Joliot Curie in Paris performed an experiment with more care, repeated the experiment, and realized that the radiation they were seeing was very penetrating. They saw that it passed through layers and layers of lead. So they also put it down to gamma rays. And they concluded that it produced very energetic. They also did a further experiment. They let the radiation fall on paraffin wax, which is a hydrocarbon very rich in hydrogen. And they noticed that very energetic protons are produced when this radiation is incinerated on paraffin wax. The energy of the protons is about 5 MeV, which is considerable, compared to the mass of the proton, which is 1 GeV. Majorana dismissed the gamma ray interpretation of this experiment. He said it was inconsistent with the momentum and energy conservation. He knew the binding energy of carbon-13. He did not know the binding energy of beryllium. It had not been measured yet. But just on the basis of this incomplete knowledge, he said it must be the neutron. Now, the neutron is a very old story. Rutherford had been speculating about the neutron for a long time. What was known about the nucleus was that it consisted of protons, but they also knew that the mass of the electron, the mass of the nucleus went up about twice the rate of the atomic number. The number of charges was not consistent with the atomic weight. So there was something else there. And one of the speculations was that it was some kind of bound state of the proton and the electron sitting inside the nucleus. But this led to other problems because the spin of the nucleus was not consistent. And Ralph Kronig drew attention to this fact that this is not a consistent explanation for the nucleus. And there was a general idea in the air that Rutherford propagated, and many others were looking for it, including James Chadwick, saying that there must be a particle called the neutron, but nobody had seen one yet. Majorana clearly said that this must be the neutron that Irene and Joliot Curie had been finding in their experiments. And this is the reaction which he said must be happening. Helium joins with boron to produce 12 carbon, not 13, and a neutron. And the neutron that comes out is the thing that collides with the nuclei of paraffin and produces protons. He discounted the fact that it could be a gamma ray. Majorana gave the correct explanation. It was the discovery of the neutron. He did not publish this result, although he was asked to do so by Fermi, consistent with his general attitude and style. Later, Chadwick got the Nobel Prize for this important discovery, quite deservedly. If you look back at the history, Chadwick himself was an amazing character. He spent about 4 years in a German prisoner of war camp, and he managed to do experiments even there. And I'm sure that people with the passion that he had deserve to get the Nobel Prize. And certainly, this was an important discovery, as we will see in the next two transparencies. Another pause for questions?
No, sir, no question yet. Everyone is so much involved, no one is posting questions.
Okay, but it'll help me because then I'll know how much people would, what can
Yeah.
focus on.
Yes.
Okay, let me go on anyway.
Yes, sir.
So the next two slides are going to show you what an important discovery this was, the discovery of the neutron. It revolutionized physics in many different directions. First, the structure of the nucleus was much better understood, and it went on to be elucidated by Werner Heisenberg, Ettore Majorana, and Eugene, the early days of nuclear physics. Suddenly it was understood that nucleus was something of a bound state between protons and neutrons, and all these things are connecting together to produce an attractive interaction that holds the nucleus together against the repulsive interaction of the protons. Bombarding heavy nuclei with neutrons, that was our further experiments. Now they were not restricted to alpha radiation. Alpha radiation is able to, of course, disrupt nuclei and cause all kinds of problems. It causes them to split up and the kind of things that we are talking about. But they are charged particles and they are repelled by the protons which are already in the nucleus. Neutrons are neutral particles and they have an easier entry into a nucleus. And bombarding heavy nuclei with neutrons led to the discovery of nuclear fission. Lisa Meitner and Otto Hahn, things like that. Chain reactions, and finally the nuclear bomb. And you can see that this has completely changed the world we live in. Right now we live in a dangerous world in which nuclear bombs are only one part of the danger. It looks like coronavirus is the other. The discovery of the neutron revolutionized physics not only experimentally, but also theoretically. Heisenberg had the idea that the neutron and the proton are two different states of the same particle. So this is the idea of isotopic spin. This was the first entrance of internal quantum numbers into physics. Now that idea led to Yang and Mills in the 1950s talking about gauge fields that correspond to isotopic spin. And that led to non-abelian gauge fields, which is a big deal in particle physics these days. All the fundamental interactions have to do with gauge fields. The better understanding of the nucleus and how protons and neutrons interact with each other led Yukawa to propose the meson hypothesis, which is another important theoretical and experimental discovery. Pi mesons were discovered later. It also led Pauli to propose the neutrino hypothesis, because when the neutron decays, and that's an example of beta decay, in a sense, you get not only the particles that you expect, but you also get a spin half particle, a neutral particle, the neutrino. The neutrino hypothesis is also very important to the understanding of weak interactions, as was shown by Fermis' theory of beta decay. And that also led to the Salam-Weinberg theory later. And finally, Landau's proposal for a neutron star is also a very amazing development. Within days of the neutron being discovered, Landau proposed that a neutron star, which is like a huge giant nucleus, is a possible state of matter. So normally you cannot have nuclei which are more than about 200 nucleons in size, because once the nucleon size gets to be about, say, 200 or 300, the number of protons in the nucleus gets very large. And that causes the thing to fall apart. I'll explain that a bit more in a second. But when you get to 10 to the 57 neutrons, what you find is that the gravitational attraction of the neutrons is able to hold the nucleus together. So a neutron star is a giant nucleus. It just has a very large atomic weight of 10 to the 57. Now, what you find is that when the atomic number gets to be about alpha or alpha inverse, alpha being the fine structure constant, which is 1 over 137, if you try to put about 137 protons and as many neutrons as you like, about twice the number of neutrons into a nucleus, what you find that the atom that you would form has got an electric field at the Bohr radius, which is strong enough to pull out electrons from the vacuum. That makes it unstable. And so there are no nuclei which have got atomic numbers greater than about 137. This is a rough dimensional argument, and you can actually check it for yourself. This is what will happen. So that there are no nuclei or atoms with atomic weights more than about 250 or 300. Uranium is 238. It doesn't get much bigger than that until you come to the neutron star, which is an entirely different proposition. So any more questions?
Yes, sir. There is one question.
Yes.
There is a question related with the particle mass difference. That it is, if there are same particles, where does the small mass difference comes from? That is a question posted by Siddharth.
Oh, okay. So the neutron and the proton are supposed to be the same particle, except that they are the same particle only if you turn off the electromagnetic interactions. So the idea is that the electromagnetic, you have a hierarchy of strengths. The strong interactions are the strongest. Then the weaker than that is the electromagnetic interactions. Then there are the weak interactions. And then there's gravity. The four known forces of nature are organized in strength. So now for a moment, the theorist turns off all the other interactions apart from the strong interaction. And the proposal from Heisenberg is that in the strong interaction picture, the neutron and the particle and the proton are just different states of the same particle. Now, when you turn on the electromagnetic interactions, some changes are made, but they are small changes compared to the strong interactions. For example, the neutron picks up a magnetic moment, the proton picks up a magnetic moment, and those things have to be turned off before you can regard them as the same particle. Thank you. I appreciate the question very much.
So there's one question from YouTube. Shubhashish Das. Please give some reference to get more knowledge about Majorana.
Yes. What I will do, one reference for Majorana. Let me think. There are some articles in the American Journal of Physics by Esposito about Majorana's work. And actually, if you just search the net, you'll find that there's a lot of interest in his. Let me think. I drew on several sources, all of which I got from the net in preparing this talk. And the one I found most helpful. Okay, let me share it with you later on. There were several sources. I'll try to put something together.
Okay, so there's one more question from Shubhashish Das. Kindly explain neutron star. How Landau through this type of large thing on that time.
Right. So Landau realized that the reason that nuclei cannot get too large in terms of protons is because of the electromagnetic repulsion. So then what he said is that the neutrons provide mass without providing any charge. So if I take the proton and keep piling more and more neutrons, at some point the number of neutrons will get so large that the gravitational attraction of the neutrons will be sufficient to overcome the electrostatic repulsion of the protons. That was his argument. But there is a catch to this. We know that neutrons, free neutrons, are unstable. They decay in about 15 minutes. So if I take lots of neutrons and put them in the star, why don't the neutrons decay? So what he realized was that when the neutrons decay, they will have to go into protons, electrons, and a neutrino. The neutrinos will, of course, escape from the star because they are massless, supposing that they are massless. They practically travel at the speed of light and can escape because the neutron star is not a black hole. But the electron cannot escape. It has a finite amount of mass. It has a mass. And once all the electronic levels in the neutron star are filled up to this level where the, the, the Fermi level for the electrons can become so large that the neutron cannot decay simply because its final state is blocked. Then you get a stable neutron star. So that's in fact how a neutron star is formed, because the neutrons in the neutron star cannot decay. They have no final state for the electron to go into. So they are forced to remain as neutrons, and neutrons in a neutron star are stable, just like neutrons in a nucleus are stable. They do not decay. Thanks. I appreciate all these questions. And I'm happy to answer more questions if there are any.
Yes, sir. There are some more questions. Chat box, Pallavi.
Yeah, there is one question in chat box. In fact, it's a doubt that as we said in physics, we bombard the particle on each other and then we get other one. So can
Yes.
we conclude that the Stone Age time, by rubbing the stones, heat was
Yes.
produced because of the particles, and that is why we got sparks?
Yes. Yeah. That is true. By hitting stones against each other, you can create sparks. And that's a very good analogy to what the physicists are doing at the microscopic level. So you can hit stones against each other, you create sparks, then you wonder what the sparks are, right? And perhaps you discover fire by doing that. So the idea of hitting things against each other, which all children know instinctively, is something which humanity has used throughout the ages in order to improve their understanding of the world and make our lives more comfortable. So you can see it even in the present time that
Mm-hmm.
fundamental discoveries in physics lead to technological innovations that make our lives better. And
Yes.
there's this constant chain of knowledge that goes from curiosity to technology, finally to our own comfort and prosperity on this planet. Okay. I hope I've answered
Uh,
that question.
yes, sir. I think it's clear. One more question, sir. It is related with the neutron star. That decaying
Yes.
process of a neutron is we are referring to. So do the small
Yes.
element like hydrogen are formed in the neutron star or outside the neutron star? This is the question.
Right. Yeah. Actually, the neutron star, uh, it's a very compact object, and the pressure is so high that atoms by themselves are in a very well. It's deep inside the neutron star. There are no atoms. It's only a fluid of neutrons. But as you get out to the outer layers, you find iron in the outer regions of the neutron star, and at the very outside, you can also get hydrogen atoms, which are in a very strange state because they're in a very powerful magnetic field, and it's practically a one-dimensional atom. So the states of matter around a neutron star are quite exotic. So deep in the neutron star, right in the center, you might even find a little bit of quark matter. That is to say, the matter which is basically quarks, basically fundamental constituents of matter. As you get out, there are more and more neutrons. Finally, at the crust, there are iron atoms. And you do find hydrogen atoms also, but in this very distorted state because of the strong magnetic field.
Strong
The
magnetic
magnetic
field.
field of a neutron star is about 10 to the 12 Gauss. Yeah, it's a very huge magnetic field. The terrestrial magnetic fields are like 10 to the -4 or something like that. Okay.
Thank you. Thanks a lot, sir. It's questions are this much only.
I think there's
Means
one more
Okay.
they will,
question.
yeah, there may be YouTube. So,
No, here only.
okay.
Yeah.
Yeah. So as you mentioned, the decaying process of neutron. So
Yes.
do small elements like hydrogen are formed in the neutron star or outside the neutron star?
Yeah, on the outside. That is on the outer surface. Deep in the neutron star, it's all just a fluid of neutrons.
Okay.
It's in fact a
That's
superfluid. According to some people, it's a superfluid because, that's way too far away from. It's true that it's considered to be a superfluid.
okay, sir. No
Okay.
questions
So
more.
Thank you.
many of the physics that you find in the laboratory here have parallels there also. In fact, astrophysics, areas of astrophysics have so much physics in them that, it's astrophysicists seem to have all the physics to apply in their field, because there are such extremes of conditions there. It could range from black holes to neutron stars to white dwarfs. All kinds of physics comes there. Anyway, I'm glad there's so much interest in neutron stars. I'll try to, at the end of the talk, I'll try to give some references for that also. Okay, now let me get on with the talk. Thank you for all the questions. I appreciate them. The second topic that I want to talk about are the motion of atoms in magnetic fields. When atoms are in magnetic fields, if the atom has a spin, there's an interaction between the spin of the atom and the magnetic field. And the work of Majorana, which I want to talk about, relates to the adiabatic theorem of quantum mechanics. So let me just start with a very simple model that describes all this and talk about this problem in the context of that simple model. We'll get back to the more realistic problem later. This is called the Landau-Zener problem, and it's a problem that was addressed simultaneously by several people. Landau, Zener independently, Majorana, and there was one more person whose name I've forgotten. Anyway, it happens to be a problem that was addressed at the same time by many different people. So here's my Hamiltonian. It's the Hamiltonian of a spin half particle. The Hamiltonian has two terms, delta times sigma 1 and t xi times sigma 3. It's a time-dependent Hamiltonian. And these sigmas are the Pauli matrices. And I'm sure you learned about these at your mother's knee. You know what the sigmas are? They are these anti-commuting matrices which square to 1. The 2 by 2 matrices. The forms are very well studied in quantum mechanics books. So the first part of the Hamiltonian is a constant. It's some delta, which is an energy gap times sigma 1. The second part is time dependent. And if I plot the energy levels of this Hamiltonian, it is the sum of the squares, the square root of the sum of the squares of delta and t xi. And the energy levels look like this. So there's a positive energy, and it goes from, as t goes to minus infinity, it becomes a big gap. And as t goes to plus infinity, it's another big gap. But as t goes to 0, the gap narrows to twice delta, which is the smallest gap between the two energy eigenvalues. Now, what the adiabatic theorem of quantum mechanics tells you is that if I vary the Hamiltonian slowly, that's to say, h dot upon h, that's roughly speaking equal to xi upon delta, is small compared to the frequency, I can take the energy delta, which is, and divide it by h bar to produce the frequency. If the rate of sweeping is small compared to the energy gap, there will be no transitions between the two states. So if I start out with the blue eigenstate, I will remain in the blue eigenstate. And if I start out in the yellow eigenstate, I will remain there. That's the adiabatic theorem. And it's strictly true only if the rate of traversal is infinitely slow. That is to say, I change the Hamiltonian slowly. I find that the system remains in an instantaneous eigenstate of the Hamiltonian. It sort of sticks to that eigenstate, clings to it, and a blue eigenstate at minus infinity will emerge as a blue eigenstate at plus infinity. However, if the rate is finite, as it sometimes is in realistic problems, there's a small probability of transition from the blue state to the yellow state. And this probability is calculated by Landau, Zener, and Majorana independently. And it turns out to be exponentially small in the gap, e to the minus pi delta squared upon xi. Now the condition of adiabaticity is in the line above the first equation. Xi upon delta is much smaller than delta upon h. You can understand this equation because xi upon delta is a rate dimensionally. And delta upon h bar is a frequency dimensionally. If a rate which has the dimension of inverse time is compared to a frequency which also has dimension of inverse time, I can ask that the rate should be very much smaller than the frequency. And under that condition, the transition probability is given by the formula below. So this result was worked out simultaneously by Landau, Zener, and Majorana. And there's a big difference in the approaches. Majorana had a very, formal, majestic way of doing things. He did some integrations in the complex plane, higher mathematics. He used Laplace transforms, and the method is entirely deductive. He came up with an answer that included some Laplace transforms, and he arrived at this answer. Now, there's a sharp contrast with Landau's method. Landau's method used low cunning rather than higher mathematics. He also went to the complex plane, but he went to the point of degeneracy. In complex time, there's a point at which the two levels merge. And he used that, the topology of that and the physics of that degeneracy point, which is actually not a real point, it's in the complex plane. And he used that to infer his results. Anyway, they both got the same answer. But one difference with Majorana, he started with a problem which was a spin S in a magnetic field. Not spin half, but spin S, a general spin. He quickly realized that you could reduce the spin S problem to a spin half problem by simple algebraic manipulations. So you only have to work out the answer for spin half. And you can take the spinner of a spin S and think of it as decomposed into a lot of spin halves and get the answer that you see in the realistic laboratory context by some algebraic manipulations. You don't have to work any harder. This is an early example of non-abelian parallel transport. From a more mathematical point of view, he was one, in some ways, thinking of the Hamiltonian as a gauge field that performs a rotation in the internal space of space. So this is quite remarkable that he thought of this in 1933, whereas we only think of non-abelian gauges much later in the 50s. Now today in cold atom laboratories, atoms are trapped using magnetic fields, and they manipulate the atoms and do all kinds of things. And these people who do that, and there are some of them in my institute, my colleagues, Saptarishi and Sanjukta, they have to account for Majorana losses. So what happens is that when an atom goes through a trap, it goes up and down, oscillation. As it goes through the bottom, the magnetic field changes. And this changes of the magnetic field can cause spin flips. And it's only one of the spins which is trapped by the magnetic field. The other spin is actually repelled. And so you lose atoms from your cloud. And the problem of Zener and Landau-Zener, the Landau-Zener transition is also relevant to solar neutrinos. They are born in a certain flavor in the middle of the sun, but when they come out, they seem to have transmitted to a different flavor. So this is a problem which has applications not only in the laboratory, but also in astrophysics. And in fact, understanding solar neutrinos also led us to understand that neutrinos do have a mass, which is contrary to the standard model which was current before that. So that ends the part which I'm talking about atoms and magnetic fields and the adiabatic theorem. And I'll pause again for questions about this part related to the adiabatic theorem and atoms and magnetic fields.
Hello, sir. One more question related with the neutronless beta decay. Our participants are seeking for the explanation for the seesaw mechanism and neutronless beta decay.
I think you
Neutrinoless.
mean neutrinoless.
Yeah, it is neutrinoless.
Yeah. It's basically, okay, I'm a little rusty about this, but you can think of beta decay as essentially a neutron going to an electron, an antineutrino, and a proton. That reaction conserves everything. So in a sense, what you do is you take the two neutrons, and the two neutrinos can be replaced. In a Feynman diagram, the two neutrinos can be replaced by an exchange of a Z naught, that is to say, a neutral current. I think that's the rough explanation for what maybe I'm not very good at this. My memory is a bit rusty, but basically there's something called neutrino-less double beta decay, where you get two neutrinos basically, and you can combine them into one neutral particle. I'll do a better job of answering this after the talk and check up on it, and I'll answer your questions on the chat. Yeah. So yeah. Any more questions?
Uh, yeah, one more that how this experiment is lead to the mass of neutrino.
Yeah. So in the standard model, the neutrino did not have a mass. And what happened with a better understanding of the sun, we started developing a standard model of the sun. People understood the sun in such detail that there were more and more puzzles. The problem was that neutrinos which were supposed to be emitted by the sun according to the standard model of the sun were not being detected at the earth according to the standard model of particle physics. After some years of this annoying conflict, it was realized that neutrinos were oscillating from one flavor to another. They were being born as one kind of neutrino inside the sun, that's the electron neutrino, and they were being converted into another kind of neutrino when they arrived on Earth, a different flavor. There are these three generations of particles in the standard model, and this oscillation has a certain length scale. It's a certain length scale over which the flavor oscillates from one kind to another. Now, this length scale corresponds to the mass of the neutrino. If there's no neutrino mass, there would not be a length scale of oscillation. It would go to infinity. By this usual relation, that length scales are related to the mass by h bar over mc. Yeah. So that told us that the neutrino actually has a mass. And it's an experimental fact that neutrinos seem to oscillate from one flavor to another. And that requires a mass for the neutrino. And this was not there in the original standard model. And clearly there's new physics beyond the original standard model. And for many of these questions, I could actually suggest that you should ask Amol Dige, who's one of the people who were with us, who was with us in the Olympiad. There are many people in India, but Amol Dige is one of them. You have him right in Bombay. And you just write to him, he'll give you a much better answer than I can give.
Sure, sir.
Yeah.
We'll do that.
Okay, let me get on with the talk now. Let me try to wind up. I've got about, actually I started at 4:20. It's about 5:16 now. But I think we've had enough questions during the talk that I can go a little bit into the question time, if you don't mind. I hope that's okay.
Yes, sir.
Yes,
Fine.
sure.
So finally, the last topic is his most famous work. It's unfortunately a little bit more advanced than the two topics I've talked about, both of which involve only elementary quantum mechanics. This one involves a little bit of particle physics and field theory, but I think that the master students will have no trouble with this. And this is the discovery of Majorana particles, the proposal of Majorana particles. Now, it was a very famous work by Dirac, where he proposed a relativistic theory for the electron. Schrodinger's equation, which is written here on this slide, gives a different role to space and to time. There's only one time derivative, and there are two space derivatives. This is unsatisfactory, because in relativity, space and time are really on an equal footing. Minkowski unified the two in space-time. So we should not have such different treatment for space and time. Dirac proposed an equation which has one derivative in both. And it has the same form as the Schrodinger equation, except that the Hamiltonian is linear in the momentum, and therefore there is only one derivative. Now, the Hamiltonian is linear in the momentum, but it is not a scalar, it's a matrix. It has to be a matrix, and in order for this equation to work. And as a consequence, psi has to be a vector. The wave function has to be a vector. And psi being a vector is actually good because it includes electron spin automatically. And this was one of the triumphs of theoretical physics, Dirac's proposal of the Dirac equation. We haven't seen work of that class for a long time. So Dirac's equation looks like this. There's a term which is gamma mu d mu psi plus m psi equal to 0. M is the mass of the electron, and it was a equation designed to represent electrons. This is in some sense the square root of the Klein-Gordon equation. If you square the operator on the left here, you will get the Klein-Gordon equation, provided the second equation is valid. The two gamma matrices, which are 4 by 4 matrices, anticommute with each other. I mean, the commutation, anticommutative gives you the metric. So when you square the equation, what you find is the Klein-Gordon equation, which is a truly relativistic equation, which describes spin zero particles. Now the gammas are complex 4 by 4 matrices. And they are written here. Gammas are written, gamma naught is sigma 3 times the identity matrix, which is a direct product of two matrices. When you take the direct product of two matrices, you get 2 by 2 and 2 by 2. You should put blocks there in the 4 by 4 matrix, and that's why you produce the gamma naught and the gamma j. And this equation gives you a wonderful description of electrons, and further it is the basis for the theory of quantum electrodynamics. Now this equation necessarily has complex solutions because the gammas here are complex matrices. And if you want the equation to have a solution, you find that psi has to be complex. Now that's completely okay when you're describing the electron, because complex fields describe charged particles and the electron is charged. When you have this operation of charge conjugation, the electron goes into a positron, which is also charged, and that is different from the electron. So what you find is that when you solve this equation, apart from the positive energy states, you get the negative energy states, which have got negative energies. And Dirac postulated that the negative energy states were all filled and the positive energy states were all empty in the vacuum. So if you promote an electron from a negative energy state to a positive energy state, you get a hole in an electron. So it simultaneously predicts the correct properties of the electron and also predicts that there must be positrons. And Anderson discovered the positron. So this is a very good theory, one of the most beautiful and elegant theories that we have had to date. So electrons are different from their antiparticles. Just after the Dirac equation was proposed, it was clear that the electron is a Dirac particle and it has an antiparticle which is distinct from itself. But this is in sharp contrast to the photon. The photon is its own antiparticle. If you take the charge conjugate of a photon, you get back a photon. Photon is described by a real field, that is the Maxwell field, electric and magnetic fields. Also, we have neutral pi mesons and gravitons, all of which are described by real fields, and they are their own antiparticles. Now, you notice that all these particles are bosons, and it looks like bosons can be described by real fields. So the question that Majorana posed is, can I have a fermion which is its own antiparticle? In other words, can I have what we call today a Majorana fermion? So can fermions be their own antiparticles is the question he asked. And it was a slightly insightful question. He was asking whether such a thing is consistent with special relativity and quantum mechanics. And the answer he found is yes. Actually, the difficulty is not in the answer, but in the question. He asked a good question. And once you ask a good question, you can answer it. He found a set of gamma matrices which satisfy all the conditions that Dirac wanted. The anticommutative of two gamma matrices gives you the metric. Now, the difference between these gamma matrices and Dirac's matrices is that all these guys are imaginary. You learned that sigma 2 is pure imaginary, whereas sigma 1 and sigma 3 are real matrices. You can see that gamma naught has got one sigma 2, therefore it's imaginary. The second one has got an I, that makes it imaginary. Gamma 2 also is pure imaginary. And finally, gamma 3 has got two sigma 2s, which makes it real, and one I, which makes it imaginary. So now if you look at the Dirac equation restricted with gamma matrices replaced by Majorana's gamma matrices, you find that the equation is real and you can have purely real solutions of the Dirac equation. or rather the Majorana equation. So the idea that a fermion can be its own antiparticle is consistent with relativity. That is the great insight of Majorana. Can neutrinos be Majorana? We really don't know. We don't have enough experimental data to decide this. So that's one of the open questions, which is still under research, well, a matter of current research. But there was another insight that Majorana had in this context. He was trying to write a Lagrangian for Majorana fermions. For the Dirac equation, you can write a Lagrangian, which is basically psi bar gamma mu d mu plus m psi, some such thing. I mean, there's a standard Lagrangian that you can write. When he tried to write a Lagrangian for Majorana fermions, he found that he needed to use anti-commuting variables. These are Grassmann numbers, numbers where 2 times 3 is equal to minus 3 times 2. I mean, I'm giving an absurd example. It's not true for ordinary numbers. When you count potatoes, you don't have such. When you balance your bank account, you don't use Grassmann algebra. But that's what Majorana did in this case, 50 years ahead of his time. That tells you how deeply he thought about things. He was using variables which were anti-commuting long before they were needed in theoretical physics. So the left and right-handed parts of Majorana particle are complex conjugates, and the equation can be rewritten in this form. This gamma mu d mu psi of the left-handed part. The left-handed part is just 1 plus gamma phi by 2, where gamma phi is the product of all the gamma matrices in a line. Has got psi L as well as the right-handed part, which is the complex conjugate. So the equation looks like the one you're seeing on the screen. Now, this seems to violate phase symmetry. We normally have in quantum mechanics, when you have a wave equation, you can multiply all the things by e to the power of I lambda, where lambda is an arbitrary phase, and it still makes sense. You can't do that here. If you multiply psi by a phase, you have to multiply psi star by the opposite phase, and this equation will no longer be relevant. It seems to violate phase symmetry and gauge invariance. But this is going to be important. You notice that there's one phase symmetry, a residual phase symmetry, which is still allowed by this equation, namely multiplying by a real phase. Now, the only real phases are 1 and minus 1. Minus 1 times minus 1, if I multiply this equation by minus 1, it will still be true. So it's not as if the U1 symmetry is broken, U1 gauge symmetry is broken. It's broken down from U1 to Z2. It's not broken completely. But in superconductors, gauge symmetry is broken from U1 to Z2. For example, there are Cooper pairs. 2 electrons put together form a Cooper pair, and the gauge symmetry is actually broken not to nothing, but from U1 to Z2. So you can have in a superconductor Majorana particles, which are excitations, quasi-particles there. In a superconductor, you have electrons interacting with the bosons, with a condensate. And in the presence of a condensate, electrons lose the identity and might actually become the holes. There's no real difference in a superconductor between electrons and holes. So one could think of a superconductor as a place to look for Majorana fermions. The search has been going on experimentally. Finally, I'll conclude with a few remarks. Like most of his friends in the Fermi school, who were called the Anisperna boys, this school was named after the street in Rome where they had their laboratory. Majorana was rooted in experiment. He was very conversant with experimental techniques, what was known at that time. But in theoretical physics, there's also a need for imagination and conjecture. You need imagination to formulate hypotheses, which can then be tested. So in order to do theoretical physics, you need wings as well as feet. Your feet remain on the ground, whereas your wings make you soar and see a landscape far beyond what you see in the laboratory. And this is where Ettore and Majorana excel. So with those words, I'd like to thank you for your attention. And I think I've got, I've used up my time. Thanks for all the attention and the questions. Thank you.
Yes, sir. Let's just see if there are any questions.
No, sir. Right now there are no
Yeah, I'm
questions.
just
Actually,
checking the
most of
YouTube.
check for the YouTube.
Okay.
There are no
So
questions on YouTube, sir.
Okay.
So thank you, sir, for the wonderful lecture. In fact, we had lost track of time. It is you who were telling us the time. Uh, there's one more important thing for all the participants. The feedback form is put in the chat box, so please fill it up. Uh, Now I call upon my colleague Amit More to propose the vote of thanks.
Yeah, before I propose the vote of thanks, there is one question that I just saw in the chat box.
Yeah,
Yeah, yeah.
By,
just now
does
it
it
came.
mean that the charge particle can't be described by real field? This is a question by
Yes.
Shailesh.
Yeah,
Does
that's
it?
correct.
No.
Yeah, charge particles have to be described by complex fields because when you do a charge conjugation, every field is replaced by its complex conjugate, right? And so a particle will go to its, a positively charged particle will become a negatively charged particle under charge conjugation. So real fields only describe neutral particles like the pi zero meson or the graviton or the photon. I mean, these are all bosons and they're all real fields. Yeah, that's correct. And let me just add, I will, some of the questions which I could not answer, I will send an answer after looking up the internet to Shaker, and perhaps he can forward that answer to the people who asked that question. I'm not really
Sure,
sure.
sir.
Uh, so
Yes,
one
sir.
more.
Yeah,
Uh,
yeah.
s-
Pallavi.
Yes.
so one more.
Request.
Yeah, one more request actually. It is about some reference. If you can give us some reference
Yes, yeah. That
related
too
to the topic.
related to which topic?
This Majorana particles and related
But
topics.
Because you said
right.
you will give it at the end, so I think
Yeah.
that's the question, sir.
Okay.
Yeah. Right. I'm not so organized that I keep my references in a good form. I'll have to just go to my computer and look for it, and I'll do that. So thanks very much for your attention. I'm really happy that the Physics Associate, I mean, the
IPT.
IPTA, is so active at this time when everybody else has, life seems to have come to a halt. But I'm glad that physics is surviving in these difficult circumstances. Just as I told you the story about James Chadwick, he was able to do physics in a prison camp. Surely we are all in prison right now, and we are glad that you're managing so well. Thank you.
Yeah, sir. I have one question, just about your last slide. You mentioned about the Majorana particles. Uh, is it the behavior of electron at the transition temperature in superconductors? They behave like a Majorana particle.
Yeah. In a sense, that's the theoretical expectation. People have been looking for this in topological insulators, which are also superconductors. That's a very active field of research. That there's a connection between superconductors and insulators, and they're looking for Majorana particles and their signature in these things. There are claims that they have been found, but I mean, it's not universally acknowledged. No? Here, this is all a theoretical argument. What I'm presenting here is a theoretical argument that the gauge symmetry is only partly broken inside superconductors. So you can have Majorana like quasi-particles. They're not actual particles. It's an electron dressed with the superconducting condensate.
Okay, sir. Thank you. It was indeed
Okay.
a wonderful and enriching
Stop
experience
sharing my
to
screen.
listen you.
May I stop sharing my screen now?
Yes, sir.
Yes,
Yes,
sir.
sir.
Yes.
So it was very interesting and mesmerizing to know about Ettore Majorana and his work. Let me be honest to say that I first time come to know about this genius physicist and his contribution in physics. Sir, you very simplified manner you explain many aspects of particle physics and Majorana particles. Uh, I, on behalf of Mumbai Sub-Regional Council, IPT, and Department of Physics, KJ Somaiya College of Science and Commerce, I thank you for taking out time from your busy schedule and making this evening a memorable one. Thank you so much, sir. I also thank our management and principal for their constant support in conducting such kind of activities. I thank our president of IPT for such a unique idea to be connected with the physics learner across the country in this pandemic time. I thank Mr. Santosh Kundu and his technical team for enormous efforts behind the curtain. And I thank all the participants for the patience listening. I thank you, everyone. Thanks a lot.
Thank you.
Yeah.
Is Santosh there?
Yes, sir.
Can
Yeah,
you
sir.
play us the campus digital this thing
Yeah,
so
yeah, yeah.
everybody
Just
can have a look at?
just a minute, sir.
So we have a lovely campus.
Yes.
So just a virtual tour of it.
Okay. Okay. Look forward to seeing it.
Or Amit, do you have that clip? You can
Uh,
play it.
just I'll try. I'll try. But no, I'm not having right now in my
Just a
device.
minute. I'm sharing it, sir.
Oh, I think that's it. Uh, thank you, sir, very much. Thank you, sir, very much for a wonderful talk. And it's a pleasure hearing you. So I think you muted your mic.
Yeah, I
Yeah.
unmuted it. Yes.
Yeah.
So thanks very much for the invitation and all the best to all of you.
Hope so.
Thank
We
you.
will
I really
continue
enjoyed
with this association in future.
Yes. Thank you.
Okay, sir. Thank you.
Bye.
Yeah, we can leave the meeting now. Santosh, you can end the meeting.
Okay, sir.